Hey everyone, thank you for joining us for this Esri plus Python Spatial Data Science overview today. We're really excited to have you join us, and just so you know a little about who we are, I'm Shannon Kaliski, and I'm the Product Manager of Analytics and Data Science across ArcGIS here at Esri. And with me today...
Hello, I'm Oren Adam. I'm a researcher in the Spatial Statistics team.
I'm Yongyao Jiang. I'm a software engineer in machine learning on the Python API team.
And today we're going to walk you through some of the basics of spatial data science, and Oren and Yongyao will go through some deeper dive demos into spatial machine learning and using deep learning with spatial data. So let's get started. First and foremost, what is spatial data? And essentially, you can think about it as the use of spatial methods and algorithms to analyze data, find patterns, make predictions, and build better models. So we integrate with many open source libraries, frameworks, and platforms out there, including Python, and we have some of the kind of a mismatch of libraries and packages here. So you see scikit-learn and TensorFlow, but we also support R, IBM Watson. We integrate with Microsoft AI, and you'll see a lot of our use of Jupyter throughout today's presentation. And then on our side, we have special spatial libraries that we have created. For Python, we have the ArcGIS API for Python that's designed to help you work with spatial data when it's in REST service form. So that's a web endpoint that you may be accessing. And then we have ArcPy, which was originally designed to work with our native geospatial software. So we've been in the business of doing spatial analysis for a really long time. And over that time, we've created a lot of tools and algorithms that are really optimized to be able to solve spatial problems. And that's what ArcPy really unlocks for you. And all of this can be used seamlessly in one environment back and forth. Oh, and for R, of course, we have the R ArcGIS bridge so that you can do R analysis side by side with spatial problem solving. So let's get started. Let's jump right into it. So I want to start with this idea of data engineering. Now, if you're coming from a data science background, you may think, I think you have a missed word there. I think it should be feature engineering. And if you're a GIS person, you may be thinking, I think you meant data wrangling. But actually, no, I mean data engineering. And here's why we're using this term. So if you think about a modern spatial data science or a modern data science workflow, particularly data science around machine learning, when you think about that table of data that you're working with, those columns are called features. And all of the values under there are ways that you want to look at those values, want to look at the rows and improve those features. So when you talk about feature engineering, you could be filling in missed values. You could be dropping fields that are either duplicates or just not helpful to the analysis. But on the GIS side, we don't call those features. We actually call those attributes. The columns across the top there, so in this particular pandas data frame, you see arrest, date, year, month, last name, all of those attribute values. We call it that because it's describing the data. Now you may be wondering, why not just call it features then? And it's because in the spatial context, we consider features to be the complete data set. And these can be points, lines, polygons, or even more complex geometry, so multi-point or multi-line feature. So when you put all of that together, the tabular data plus the geographic representation of it, that's when you have a feature in the GIS side. But all of this ultimately, in the end of the day, is data. So that's where we came up with data engineering. And all it is really the process of turning raw data into analysis-ready input. So this could be wrangling or cleaning the data. It could be geocoding, which is the process of taking data that's not yet spatial and making it into spatial. A lot of times you'll hear us call this location enablement. And you can do this with an lat long, an address, a place name, so maybe a city name, or a postal code. So anywhere in the world you have different postal codes that you may be using. And really the more specific you are on that location, the more accurate that geocode is going to be. And then you get actual feature engineering, which even though there's a difference in terminology, it still applies very well to GIS. And many GIS analysts have been doing this for years. And it's kind of that high-level process of refining the data attributes. So you may be doing things like field calculations, taking two of those columns and adding the values to create a new one, or taking a field and creating a dummy value off of that. So I'll show you an example of that in just a second. But the idea behind that is that machine learning algorithms and many analysis tools don't actually work very well with text fields. They want numbers, especially if they're doing math. So creating a dummy value is really doing that, is taking something, maybe it is a danger classification, and turning that into a number, maybe 0 to 4. Then in the GIS world, we have things like overlay analysis, where you can actually clean data by looking at how it intersects and interacts with the data around it. We already talked about filling missing values, and there's many other things that could fall into this category. It really depends on the data that you're working with and what you're trying to do. And then we have this concept of geo-enrichment. So if you think of geocoding as giving you new values, you can think of geo-enrichment as adding attributes to the data set that you already have. What this does is gives you more context and a deeper look into your data. And this can be over space and time. So even if you think of something as simple as demographic data from the census, that has a specific space and time that it's relevant to. And if you put many of these data sets together, you can start to understand how things change over time, how populations move, how the impacts of decisions that you're making in your organization. Maybe you're on a mission to end homelessness, and being able to map that population over time will be able to, and enriching that with the information from either the lifestyle of the community, will really give you a complete picture of if you're actually getting the results that you were setting out to get. Okay, so now let's take a look. Now for my demos, I'm going to keep them pretty simple, but remember, Oren and Yang will be diving really deep a little bit later to show some more complex use cases. So let's take a look at this notebook. This is an ArcGIS notebook that is hosted within my geographic system. And from this, I can do everything that I would expect to be able to do in a Python notebook. So looking at the first cell, I load in my libraries, I bring in my raw data, and then, of course, I make a map. Now, this notebook is all about the Naʻahele trails, which are the state trail program in Hawaii. Some of these trails are ancient, and as you can imagine, that has some particular challenges around it. They also can be hazardous. Hawaii is a volcanic island, and there are many hazards that can go along with that. People can slip on rocks, people can encounter lava. And so because this is also a very popular tourist destination and a mecca for doing research and environmental preservation as well, you can imagine being an analyst tasked with solving the problem of creating an index that people can use to understand how dangerous each trail is. So for that, we'll want to look at data. So here we see our data in our pandas data frame, and we can already see perhaps a potential problem. This field for the link has parentheses, which may cause problems later on. So here we go ahead and remove that. And as we look through the data, we see that there's different data for hazards and for the features that they may see. So when we start charting this out and we look at the standard is how difficult the trail is to traverse. We can see another problem, very common in many data sets we'll work with. This data has difficult, moderate, and easy clearly marked, but has a number of values that are completely unknown to us. There's no value there. And there's fields that say not applicable. And we don't know what that means. There's no information in the metadata to tell us if not applicable means that it is easy, if it's difficult, if it's moderate, and we want to make a classification. So what we can do is go through and create a definition where we change the level of the difficulty so that we populate the value from unknown. replacing the blank fields with unknown and changing NA to also unknown. And when we remap that data in Seaborn, we can see that our chart is now completely filled out, and we can represent all aspects of this data. Now, as we continue, we can see that we have all of this data plotted out, and if we look at it on a map, we now get a rough idea of how difficult the trails are to traverse. But that's not enough to get a complete danger index. These trails also have a number of hazards, and when we looked at the data, we saw that some of these were quite verbose. So you can see there's hunters, there's cliffs, there's landslides, there's bees. To put that text in and try to add it to this new difficult moderate NA would not make for a very useful analysis. So to engineer this data, we'll go ahead and just make it a very binary field, 0 for no hazard, 1 for there is a hazard. And when we take a look at that on the map, we can see that most trails do in fact have hazards. And then by doing a simple calculation to add our danger field to our difficulty field, our difficulty to our hazards, we can create a field for danger. And when we draw that on the map, we now can see which trails are going to be the safest for us to recommend to tourists, new researchers, and which ones we might want to send a guide on or have a better understanding of. And this is a very simple analysis where we could dive much deeper. Now there's also a way that you can do this very spatially. So that one we were tackling the attributes. But if I go and open this notebook for gun crime, we can look at a way that we can use spatial tools to clean data. Because a lot of times what happens is you have the information in an attribute table or in your feature class, but as you start to run through it, you find that the table is a little bit misleading. So this data is gun crimes within Baltimore, Maryland. So when we look at the neighborhoods, we can see that we have a number of different neighborhoods here. Actually, 208 neighborhoods have gun crime. And then when we bring in our data set for our neighborhoods, we can see by just simply running a shape, there are 278. So good news for Baltimore, not every neighborhood has gun crime. Bad news is the vast majority of them do. Okay, so let's take a look at this on a map. There we go. So we can see that we have a lot of data sets, a lot of data points for gun crimes that are falling outside our study area. Now, if we were to process our analysis with this, we wouldn't have the most accurate results. So we need to get rid of this. And one of the easiest ways to do that is to simply run an overlay. What this is going to do is it's going to allow us to use those neighborhoods as the mask for the rest of this data. So we're going to drop any points that don't fit our criteria of specifically looking at these Baltimore neighborhoods. Oh, I just need to rename that because it already exists. And while we wait for that to finish, we can see that all of the data in this map is fully interactive. So we can click on it, explore it, and learn more information about the crime that was committed or about the neighborhood. Oh, and it looks like that has just finished. And now we have the points that specifically fall within the Baltimore neighborhood. Now this data is ready for us to continue on with doing an analysis of gun crime in the Baltimore area. Okay, let's jump back into our slides and continue on. So visualization and exploration is the next step of a lot of analysis. You can really think about this as a key in the exploratory phase. It can help you visualize spatial patterns, see the trends, look at outliers, and find anomalies. So you can do this for both the raw data. So you saw with the gun crime, we had the raw data come in, both the polygons for the neighborhoods and the points, and then we cleaned it up. But you also can explore this in maps and charts and through animation. So you can see there's an animation going on in the background here where it's actually looking at the oxygen levels in a subterranean basin. So now let's take a quick look at how that can work. So we'll go back to our notebook environment. We'll quickly create a brand new notebook. And let's look for some data. So I can quickly find any of the spatial data that I have within my organization. So for this one, I'll look for some active permit data. So this data has to do with oil and gas permits. So now that automatically created a Python snippet for me where I can just rename what I want this to be. And then we can go ahead and start looking at it on a map. This is in the Permian, so I'll go ahead and focus my map on Texas. Pass it that, and let's draw our map. Now, where a lot of people stop in spatial analysis or even just working with location data is they stop with right here. They stop just with the points on the map, and they have a bunch of dots, and that's it. But the problem that we have here is this doesn't actually tell us where there are true patterns. We just have a clump of points. So to be able to understand what the patterns are in a very quick visual exploration way is we can use an analysis tool. So if I go to Analyze Patterns, I can quickly pull in this Find Point Clusters tool. So this allows me to look, I can see the signature, see what this tool does and what inputs I would need to do. But this allows me to define what a cluster is. So I can pass it an analysis layer of those permits. I'll tell it how many points represent the minimum cluster. So let's say 10, and we'll give it an output name. And we'll go ahead and let that run. And while that's running, let's go ahead and continue to write a little code. We'll remove the layers that we have on the map, and we'll go ahead and add in the results of our analysis. In just a second, that will update. There we go. And now we can see in this spatial data frame where we have patterns that meet our definition of a cluster, and the light gray points have now become smaller and a little more faded, and these are just points in a noise. So very quickly, I'm able to see where I should start to focus my activity. Maybe I want to look at this kind of tighter density of clusters right here, rather than looking at the clusters that fall maybe more to the east in this area. So that took just a few seconds, and I was able to look at the visualization for that data. All right, spatial analysis is the next step. And spatial analysis can represent so many parts of a spatial data science workflow. In its simplest form, it's really about understanding how different data sets relate to each other over space and time. And this could be different points within the same data set. And you may be answering a question like, what is the location proximity relationship of these points? But you can also do a lot more. Spatial analysis can help you do pattern detection, space-time analytics, prediction, suitability analysis, which is something that we see a lot of people in the data science space looking to do, and really seeing them combine that with prediction so that you can predict the most suitable location. And that's something that if you're not using a spatial tool, it can be really challenging to create the most representative model that will give you the most accurate results. Then you also have things like routing and logistics and terrain analysis. But let's take a little closer look at these top three: pattern detection, space-time analytics, which you can almost think of as maybe a subset of pattern detection, but it also could tie into prediction too. But let's take a look at these three. So when we think of pattern detection, we're most likely thinking of clustering, and we have a number of tools within ArcGIS that are designed to help you identify clusters based on the type of problem that you're trying to solve and the type of data that you have available to you. So you can see a bulleted list of different tools that we have through ArcPy, and some of these are also available through the ArcGIS API for Python as well. Then there's space-time analytics. And this is really all about analyzing the spatial and temporal distribution of data simultaneously. So if you think of the way we would have had to do this in the past, you would have a data set, and maybe this data set spans multiple years or multiple decades. And to complete this analysis, you would have had to run that multiple times and then merge that data all together. and then perform analysis on top of that. But this lets you do that all in one step with the concept of a space-time cube. So a space-time cube not only takes your X and Y, where the point happened, but it gives you a Z of time. So when did it happen? And you can see that one pillar could kind of represent one location over time, and then in that third little pillar you see how the points are distributed in there. And then from that you can do analysis, such as identify hotspots and see how those hotspots changed over time. Were they becoming hotter? Did they become colder? Are they oscillating between hot and cold? And this can help you when you're making decisions such as forecasting or just trying to understand the nature of a problem that you're trying to solve. And then there's prediction. And when we think about prediction, we often are thinking about something like regression or classification. Within ArcGIS, we also have other predictive analysis tools that can help you solve these problems. Whether you're trying to predict the values in a data set that has a lot of holes in it, or you're trying to predict something like the health of a palm tree or anything else using deep learning. But with that, I'm going to go ahead and turn it over to Oren to tell us some more about spatial machine learning.
Thank you, Shannon. All these amazing methods you've seen, especially in terms of analysis, we can really talk about two distinct methods. One, we can say a set of families that we can consider traditional machine learning. These are functionalities that you can find in external platforms such as scikit-learn, R, or TensorFlow. In addition, as you know, space is very close to our hearts. We have spatial machine learning methods that incorporate some representation of space and also time or space-time in the formulation of these methods so that we can treat space more than just an input, but at the algorithmic level. And to highlight the distinction between these two types of different machine learning approaches and how you can make use of these in your GIS analysis or spatial data science analysis, I will go ahead and demonstrate a regression workflow.
Let me pass this over to you.
Thank you. So I will demonstrate a regression workflow that starts with real-world data. Using analytical tools in ArcGIS platform, we will perform climate predictions. Even though this is a niche topic, from a spatial data science perspective, it's a regression problem. I'll be talking about calibrating simulated climate variables with observed temperatures so that we can predict weather in the future. This is a process called downscaling. This problem involves finding relationships between simulated climate variables and observed weather, such as temperature and prediction at weather stations. So pictorially, this is a big regression problem where we're trying to find relationships between a large set of predictors and a target variable such as temperature, the variable that we would like to predict. We will work with climate data for a contiguous United States, where we have 19 different simulated climate variables. And if you're curious, you can see the list of all the variables we use in the bulleted list here. But to step back and talk about the spatial data science perspective of this problem, I think this figure summarizes the best, where I have 19 predictors. GCM stands for Global Climate Model. These are simulated variables. And I want to use a statistical model to create a regression, a relationship that relates these 19 predictors to a variable I'm interested in, such as average temperature. Because if I have this statistical model, I can simulate these global climate variables into the future, and using my statistical model, I can actually predict future temperature. And today, I would like to really juxtapose non-spatial machine learning and spatial machine learning. On the non-spatial side, I have support vector machine, ridge regression, and random forest. And from the spatial perspective, I have the following spatial regression algorithms. First one is geographically weighted regression, also known as GWR. And the second one is empirical Bayesian-Kriging regression, also known as EBK regression. ArcGIS platform contains spatial machine learning methods, just like the ones I mentioned, and also non-spatial machine learning methods, such as random forest, linear regression, K-means clustering, to name a few. Also, if you have a Python library that you would like to use in your spatial analysis, this is very easy to do as well. Python is our native language, so integrating other Pythonic platforms for spatial analysis is very easy. Firstly, I will start my analysis by importing all the libraries I need. I will import Seaborn, Pandas for my data manipulation and visualization needs, and I will also import ArcGIS Python API that enables a seamless connection to ArcGIS's analysis and mapping capabilities. Lastly, I will import machine learning libraries I need. I will use scikit-learn to integrate support vector machine and regression. I will also import what I consider to be a spatial machine learning library, ArcPy, that contains our analytical libraries for spatial analysis and spatial machine learning. Using the Python API, let's visualize the weather stations and take a look at our problem. Like we all know, the first challenge is what Shannon mentioned to be data engineering or future engineering, or we might be calling data wrangling. Using the Python API, I can visualize the data set that I'm working with. Weather stations, which are depicted in black colors, and also the weather simulation grid that are depicted in orange. The first challenge I have here, weather stations can be down at certain times. For example, at a given location and at a given time, I may not have any measurements. We can either drop these values or we can impute or fill these values in. When we're working on a spatial problem, we need to consider the space if we want to fill these missing values. The second data engineering challenge comes when I want to combine the global climate model and the station data. Currently, the orange and the black dots are not aligning in space. So I need a way to assign the simulated climate variables in orange to where I have my station data in black. Before going forward with my analysis, I will bring all the necessary data to the environment that I'm working in. And this is a helper function here that is going to bring in all the data sets I need. So this is just a utility tool, so that I can start the first step of my analysis, which is data wrangling. Firstly, I will read in my station data, and ArcGIS Python API allows me to read this in seamlessly and represent it as a pandas data frame. So I can use a function like head that works on pandas automatically on the spatial data I have. Note that some stations have missing values that are denoted with -9999. Since the weather station data is sparse, I don't want to throw these out, but I want to fill these in. I will use a spatial data wrangling function called fill missing values in ArcPy that can fill missing values based on spatial or spatiotemporal relationships. For instance, I can fill a missing temperature value at a station with an average of values from 10 of its nearest neighbors, 10 nearest stations. Or I can also fill missing values at a station at a given time from previous measurements, such as the past month. Here I will fill missing values from 6 nearest neighbors. So I define that I will be using k nearest neighbors to fill the missing values, and I will use 6 nearest neighbors. But for your analysis, the possibilities are quite vast in terms of the way to fill your data. And after I run this function, let's take a look at the resulting spatial data frame. Now we see that all these previously missing values, such as the first column, now they all have imputed or filled values. Let's talk about the second challenge. Before I do so, let me also visualize the output of fill missing values. And in this map, here now you can see the dots in red that indicate station data that is filled. So previously this was a -999, but now I have a value assigned to it, thanks to this spatial data wrangling function. So on this map, I have my simulated global climate variables on the green dots and my station data that is not filled with these red dots. I do not have any missing values in my station data, but now how can I resolve the scale differences between different data sources? remember that simulated climate variables you look at here are not intersecting with weather stations. So how can we address that? One way of achieving this goal is to create interpolation surfaces of these simulated variables. And then we can extract these continuous surfaces at station locations to have a full data set. I will use empirical Bayesian kriging to create these interpolation surfaces. I first define all the climate variables that I have in my feature class, and these are the field names for these variables. And I perform empirical Bayesian kriging to define statistically valid continuous surfaces. EBK here is a good choice for interpolation as it can perform non-stationary kriging, meaning local patterns in my climate data, such as impact of mountains or microclimates, will be detected from the data automatically, and EBK will honor these patterns in the data instead of over-smoothing the data. And after I perform EBK regression on all of the climate predictors, now I have 19 continuous surfaces. I can simply extract values from these surfaces at station locations using another data wrangling tool in ArcGIS platform called extract multi-values to points. And with extract multi-values to points tool, for all the continuous surfaces of simulated climate, I can extract these variables at station locations. At this point, I have a fully complete data set. I have no missing station data values, and at every station location, I have the associated simulated climate variables. And when I visualize my full data using the head function from pandas, now you see that this data set is complete for regression. It contains all of my predictors, which are these 19 climate variables, and the target variable, the variable I want to predict, which is monthly average temperature. And I can use this data for training my regression models. And I want to perform regressions on an evenly spaced grid over United States. So I create a dummy data set, and I extract all the predictor values, the simulated global climate variable values on that grid. And when I visualize this grid tabularly, you can see that I have all of the global climate variables except for the value that I want to predict, which is average monthly temperature. At this point, I have a full training data set, the data set that contains all my predictors and my target variable, and also the data set where I'm going to perform a prediction. Before going in my analysis, I would like to explore relationships since this is a regression problem. So let's explore these relationships between our variables. As I mentioned, Python is our native language, so we can apply some of the common functions used in data analysis in Python directly on these spatially enabled data frames that I've been reading using the Python API. Even though this table is informative, the one thing I can do is calculate correlations between different predictors and also the target variable, which is the temperature. And I can just use the correlation function here. Again, our platform being so Pythonic and so integrated makes this very easy. And I can evaluate all these values. But I don't know about you, but I already start getting tired looking at all these values. So let's do this a better way. Let's do this the data scientist way, and let's visualize these relationships. I can use the Seaborn library to create a correlation matrix. Again, the whole process is seamless. I don't need big wrapper functions to do what I want to do. I can directly plot these in the same environment where I do my spatial analysis. In dark red and blue, you see relationships that are very strong linear relationships, meaning that if I use a linear model, it might be problematic. So let's use nonlinear regression methods. Let's first start with ridge regression from scikit-learn library. I need to define a regularization parameter here so that I don't overfit the data, and scikit-learn already has a utility function to do that. And I immediately apply this function to my spatial data set since this whole thing is seamless, and I optimize on this parameter and define a prediction. So now I have a ridge regression prediction. I want to repeat the same process with support vector machine from scikit-learn, and I fit a support vector machine model to my data. And I have some input variables here that I tweaked so that I get a perfect match to where I have station data. So on paper, support vector machine might look a little bit better than the ridge regression result because it fits perfectly to station data. But this is a spatial problem. So let's map it and see. I can also create these useful widgets as pieces of a story map, and I can display them natively in this platform, and I can interact with it. Here you're looking at the support vector machine result, the model that I tweaked so that it'll match the temperature station data. You see that I overfit the data. So this is doing a very good job of matching station data, but it's not predicting temperature accurately anywhere else. That's why I have this patchy temperature profile that is telling me that one location is in peak summer, but its immediate neighbor is in deep winter, which makes no sense. And when I move over to the ridge regression result, I already see that I was able to capture some patterns in my data, and I create a plausible temperature distribution with high temperatures in the south that are gradually decreasing as we go up north. We know that this is a spatial problem, so let's apply spatial machine learning methods as well for this regression problem. Firstly, we will use EBK regression. And for EBK regression, I use a subset of the variables. So instead of using all 19 predictors, I'm only using 3 of them. And if you're asking how did you pick those 3, these are the 3 independent variables that I picked from the correlation matrix above that are not linearly dependent on each other. However, EBK will be able to work with a larger set of variables because this is a general method. But here I want to demonstrate creating a very powerful model that already has the space inherently defined in its formulation with a small number of predictions. With a small number of predictors. I fit my empirical Bayesian Kriging regression model on my data with these 3 predictors only. So very small subset of my predictors compared to before. And I've defined my results over the prediction grid that I defined previously. So all my predictions will be in there. And secondly, I do the same analysis using the geographically weighted regression function from ArcGIS. So both of these spatial machine learning functions live inside the ArcGIS library. Now let's compare our results. But let me reiterate, both of these methods, instead of using 19 predictors, they only used 3 predictors. So let me demonstrate the value of incorporating space at the algorithm level and doing spatial analysis with spatial methods. Again, I plot my results from a widget so that I can compare these maps seamlessly. Here they're looking at the EBK result. You can see that even with 3 predictor variables, 3 instead of 19, I can capture the overall pattern. I can even capture some finer features in this data set that I wasn't able to do with ridge regression. And when I move over to the GWR results, I again see a similar profile where my model is so parsimonious that even though it has very few set of predictors, it can really capture the patterns in the climate model. And this is the value in incorporating space here. But before ending this piece, I would like to discuss another way of incorporating space that is through geo-enrichment, like Shannon mentioned. So I will explore non-spatial regression using random forest. The only difference here compared to support vector machine and ridge regression is this is the implementation of random forest in ArcGIS platform. We call this forest-based classification and regression. So one question you might have is, if this is readily available somewhere else, why did you implement this in the ArcGIS platform? Here, this tool, since it's native to ArcGIS platform, it can automatically do geo-enrichment for you, such as including rasters directly for prediction. It can also calculate distance features as predictors if you want to include them in your analysis. Here, I will first use all 19 predictors and run forest-based classification and regression to define a temperature profile. And that's exactly what I did here. I have all my predictors. And here, our random forest function lives in ArcGIS under ArcGIS stats forest. And once I define this model, I run the same model again with one difference. I add a distance feature. And this distance feature is outline of all the water bodies in contiguous United States. This will automatically calculate the shortest distance to a water body at every location I want to do a prediction on, and it's going to include it in my regression model. So I have an additional 20th predictor here. Why do we want to use a distance feature here? Well, we know that distance to a water body, such as distance to the ocean coast or a lake, does impact temperature, and that is what I'm modeling here. And one way of incorporating this knowledge is through using a distance function. And ArcGIS's forest-based classification and regression enables incorporating the spatial information automatically like that. And this is the benefit of having these tools in this platform. So let's compare the results. On the left, you will see the model that has distance features to water bodies as one of the inputs. You can see that in areas such as Washington State and Minnesota, where there are a large number of small water bodies, we actually get a more fine-grained description of average temperature because we have this geo-enriched information. And when I compare this to the result from random forest without the distance feature, I see that the features here are more smooth because I have no information to distance the water bodies to include in my regression system. So today I introduced the spatial problem with a spatial machine learning, generic machine learning, or non-spatial machine learning, and also using non-spatial machine learning methods with geo-enrichment. We see that incorporating space at the algorithm level for a spatial problem gives us parsimonious models such as GWR and EBK regression from the ArcGIS library. In addition, if you would like to test how these methods hold up against methods that you'll be using, that you have been using from scikit-learn or TensorFlow, our Pythonic interface just gives you the option to do that seamlessly. And lastly, incorporating spatial variables such as distance features through geo-enrichment can make a big difference for your analysis, for uncovering information about your data and unlocking your spatial data's full potential. That being said, I will pass the mic on to my colleague.
So while they're passing that, we know that spatial machine learning, it can be a very powerful tool, and increasingly in organizations, we are hearing more and more people want to go even deeper and explore ways that deep learning can be applied to their workflow. So, Yang, do you want to walk us through?
Sure. Thanks, Shannon. So in this demo, I'm going to be talking about how to do land cover classification using satellite imagery and ArcGIS Python API. And specifically, the ArcGIS.learn module that provides an end-to-end deep learning workflow. So land cover classification has been one of the most common tasks in many geospatial applications. So the goal is to predict the land cover class, for example, water, tree, or building for each pixel. And unlike image classification in computer vision, where we classify the whole input image as a whole. So I have picked Kent County in Delaware as the study area, and there are two input data. The first input data is a 1 meter resolution color infrared label imagery, and the second input data is a label image that contains the class label for each pixel. So this is a subset image from this label image. So the first step is to connect to your GIS. So this is just standard Python API code. You import a library and then make a connection to your GIS, which can be your enterprise or ArcGIS Online. And then we are ready to import the data through the GIS that will be used for training. So this first item is the label imagery I was talking about in the beginning. And this is the label layer, which is the label image for Kent County. So now we have the input data. We can now export the training data using ArcGIS.learn. So the idea here is to divide this large nape imagery into small image chips. For example, in this example over here, I'm dividing this nape imagery into 9 chips. But in practice, you can divide it into hundreds or even thousands of chips. And the chip size can be specified by the tile size over here. For example, here I'm setting to be 400 by 400, and this chip format is PNG. So now we have exported the chips. We can now load the chips into memory and divide them into batches using this prepare data method. By default, it also does some data augmentation like flipping and rotating to help you generate more training data. And after that, you can just call this show batch method to show you a few random chips to help you get a sense of how your data looks like. For example, in the first chip, this is trees, this is like farmland, and over here there's a road, and there are 16 of them because I set the batch size to be 60. So now we have loaded data into memory. We are ready to define the model architecture. So here we use UNet, well-recognized image segmentation algorithm. The UNet architecture and the pre-trained model has already been predefined in ArcGIS.learn Python API. So unlike Keras, where you probably need a huge code block to just define a UNet model, here you can just use this single line to define a UNet classifier. So I'm not going to get into details of how UNet works, but essentially it's just this encoding CNN plus this decoding CNN plus this cross connection, which helps it make a decision at various scales. And because of this kind of U-like shape, it's called UNet. So now we have the model. Before we start training the model, we need to find a good learning rate, which is probably one of the most important hyperparameters when training a neural network. Here in Python API, we have a learning rate finder to help you find the best learning rates for your data. So basically, it explores a range of different learning rates to see where the loss is going down very quickly. For example, in this plot over here, we can see the loss is going down. This y-axis is going down very quickly at this middle value, which is e to the power of -4. So this is what we are going to use for training. So now we have chosen the learning rate. We are ready to feed the model. So here I have fed it for 10 epochs. And as you can see, we have two values here. And this second value is the value I get from this learning rate plot. And the smaller value is what I use. It's like 1/10 of the second value is the value I use to train the earlier layers. And then I use the intermediate layers to train the middle layers, which is exactly the idea of transfer learning. So as you can see, as I train for more epochs, both the training loss and validation loss are going down. And at the end of epoch 10, we got an accuracy of about 91%, which is pretty good. So, so now we have the model ready. Let's see how it performs. You can just call it show results to show you a few like classification results in the validation set. So the left side is the ground truth, and the right side is the prediction. And as you can see, they are almost identical, although with some small difference. For example, here, this tree is more rounded, and in the ground truth, there's a few batches over here, and there's a hole in this prediction. But overall, I think we have achieved very reasonable results. So if you're happy with the model, you can choose to deploy the model to the cloud by simply uploading it to your enterprise portal as a deep learning package. All you need to do is do this gis.content.add to upload this model package to your enterprise portal as a deep learning package, and this is what you'll get, a land cover canned deep learning model. So now we have the model deployed. We can now apply the model to some new image using classify pixels method. All you need to do is just to specify the spatial extent of the new image, and then pass this extent to the classified pixels over here, along with nape imagery, and then you will get the inference result back as a new imagery layer. And if you want to visualize this inference result, you can just create a new map, and then add this inference result as a layer to this new map, and this is what you get, a fully interactive map widget. So in summary, ArcGIS.learn provides an end-to-end deep learning workflow for geospatial data, which has greatly simplified the deep learning with geospatial applications. So as you might have noticed, we are following a similar pattern as those well-known machine learning libraries like scikit-learn. So basically, we first load the data and then feed the model and then use the model to make a prediction. So if you have any previous programming experience with machine learning libraries like that, it's very easy for you to pick up and then start working with. So that's all I'd like to cover about deep learning, and I'll hand it back to Shannon.
Thanks, Anya. Now, through my earlier demos, Oren's demo on spatial machine learning, and Yangya's demo right now on deep learning, you saw a lot of examples of ArcGIS notebooks, which is the way that we have integrated Jupyter to be seamlessly available with this, alongside our WebGIS, where you can easily bring in spatial data, spatial methods, spatial tools, and have these libraries readily available for you. But for a lot of decision makers and influencers within our organizations, looking at a Jupyter notebook can feel intimidating. And even if we do the best analysis possible, if they can't make sense of it, or if they feel like it's not approachable to them, then they aren't going to be able to use our analysis to drive action. And so for that, there are many ways that you can take out the data and the information products you create within ArcGIS notebooks or within a standalone Jupyter notebook using the Python API and put that into easy information products such as a story map. So earlier we talked about Spacetime cubes. And here's a story map that could walk a decision maker, a member of the community, or anyone through this type of analysis while making it interesting, engaging, and something that they feel like they can easily understand. So you can see that the story map starts off with a story about the data itself, talks about what is needed. It integrates maps that are fully interactive, so we can search for the attribute data and understand it a little bit better. And then we can even go through and look at this space-time analysis. So a space-time cube will let them know kind of how trends are changing over time. We can see new hotspots symbolized here, consecutive hotspots. So these are hotspots that have been hot over years, and sporadic hotspots that have been going between being hot and not so hot. We can even start to visualize the data in 3D so that people can get a better understanding of how these trends are changing. And when people can understand that and even engage with it, so we can select a slice from this and understand the count and how statistically significant we are in that confidence, how statistically significant that confidence level is, and give them a key so they can understand what they're looking at here. When people are able to look at analyses such as this and understand it, then all of the work that you're doing within your organization to make these great results can be used and put into action. And the other side of this story, which we won't have time to get into today, is the role that spatial and spatial data science in particular can play in this new age of algorithms that we live in. All around the world, we're seeing people make decisions and implement machine learning and deep learning within their organization. But how many of those organizations are looking and quantifying how the input and the output of these algorithms are affecting both the human and natural world? And that's something that spatial tools are uniquely designed to do, is show how impacts are affecting society and the earth itself. So it's a really exciting time to be learning spatial data science, machine learning, and deep learning. And after this webinar, we will be sending out all of the slides. We'll provide some access to these notebooks. There'll be some blogs and other great resources to help get you started. There was a lot of questions on that. But with that, thank you so much for joining us for this webinar today. And we hope to have you back next time.